Good morning, everyone, and welcome to the third day of our GEM workshop. So some brief announcement for our schedule today. We will hear the MI coupling tutorial and then the diversity, equity, and inclusion tutorials we invited. And then also we will have a GEMI lunch in this room. So all mentors and mentees are welcome, and not only them. If you'd like to learn more about the program, please join us. And we will have also the banquet in the evening, also in this room. So if you haven't taken your posters from yesterday, please take them down because they will need to set up the room. Okay, so with this, I would like to invite our students to introduce the first speaker, Emily McDougall.
Greetings all. Our next speaker is an accomplished scientist, educated at the University of Washington, Seattle, graduating in 2009 with his bachelor's, and the University of Texas at Arlington, graduating with his PhD in 2014. He has had the distinction of being named an NSF EA PSI Fellow at the National Central University in Taiwan, as well as working at the High Altitude Observatory at the National Center for Atmospheric Research. He has an extensive background in numerical modeling and model coupling. In particular, he has an extensive amount of work developing the next generation coupled model, the multi-scale atmospheric geospace environment model, otherwise known as MAGE. In this work, he has shown that both the magnetosphere and thermosphere ionosphere response to geomagnetic storms has greatly improved through the coupling of the magnetosphere, the ring current, and the ionosphere thermosphere together. Additionally, using a coupled derivative of LFM that coupled LFM, TIE, GCM, and RCM together, Dr. Pham has assisted in examining the impact of solar flares on the magnetosphere. It gives me great pleasure to introduce Dr. Kevin Pham.
All right, thank you very much. So I'm Kevin Pham, and this is I'll quickly talk about the impact of the thermosphere dynamics on MI coupling, but first I'll go over all the tutorial for MI coupling before talking and touching on the thermosphere dynamics. All right, so what's included as part of the the magnetosphere ionosphere thermosphere coupling pathway? So you have two different pathways. First, you have the electrodynamic pathway, which is what most people know about, and that's on the left here, and that's essentially solving for Ohm's law. So you have something that gives you current, and that's equal to something that gives you conductance, and then your electric field. So typically what we do is you have the currents coming from the magnetosphere, you have conductance specified by the ionosphere, and then you solve it using something like a Poisson-like solver, and then that gives you the convection electric field or the Polecap potential. And so that's essentially what you're seeing in the picture here. The other pathway that you have is the mass pathway. This is a little bit less studied than the electrodynamic pathway, and it's a little bit more modern, and it's a lot more difficult to do. So if you take a look at this plot on the right, you can see all the different populations that are here. So they have the cold population shown in blue, you have a superthermal population shown in the teal color, then the hot population in I think that's like a gold color. they travel everywhere within the magnetosphere, but specifying these is very difficult. So they all come from the ionosphere, but how they get into the magnetosphere is a big open topic. And most of the things that's been done so far is looking at how the polar, how these ions come out of the polar ionosphere, but not so much coming out of the equatorial region, like through plasmaspheric refilling and other things like that. So this is still a region to be studied. All right, so let's take a quick look and review the electrodynamic coupling. So this is what the ionospheric conductance can do. So if you take a look at the magnitude of the Pedersen conductance, the magnitude of the Pedersen conductance controls your cross-polar cap potential. And as a result of controlling your cross-polar cap potential, that can change your potential saturation, which affects your solar wind magnetosphere coupling, or it can change, or it feeds back into the ionosphere thermosphere coupling. The other thing that ionospheric conductance can do is if you take a look at the gradient of the Hall conductance, that affects the dawn-dusk asymmetry. And so the dawn-dusk asymmetry in the magnetosphere, you can split that up into two parts. You have the meridional part, which affects the rotation of the convection pattern, and then that in turn affects the magnetotail reconnection. The other thing you can do is you can take a look at the day-night asymmetry, and that gives you the difference in flux circulation within the ionosphere and magnetosphere, and then that in turn affects the day-side solar wind magnetosphere interaction. All right, so if we take a close look at what the Pedersen conductance does and how that really changes the polar cap potential, if you take a look at the plot on the left here, the very top is a line plot of the maximum positive field line currents as a function of Pedersen conductance. So if you do, what they did here was take a look at what happens if the entire ionosphere was a constant conductance, and then take a look at how that affects the electrodynamics. As you increase the Pedersen conductance, the maximum positive field line current starts to increase slightly. And then in response, the cross-polar cap potential decreases as you increase Pedersen conductance. And so if you take a look at the bottom left plot, you get a very nice, linear relationship between that, and that's essentially Ohm's law. And then if you take a look in the middle, that's the potential pattern as a result of a constant conductance. But reality isn't constant. It's not constant. It's also not uniform conductance everywhere in the polar cap. And so typically what you actually have is a solar EUV gradient. And so the plot in the right at the top is the solar EUV gradient for the Pedersen conductance. And when you have such a gradient, you get a shift in the polar cap potential towards the night side in the bottom right plot there. All right, so if you take a look at the Hall conductance gradient, then what you get here with the Hall conductance gradient is a change in the dawn-dusk asymmetry within the magnetotail. So on the left here is a uniform Hall conductance, and then if you see in the bottom left, you can see that the magnetospheric tail is about equal on both sides, dawn and dusk. However, if you have something that looks more like a gradient in the top right there, you have a gradient in the Hall EUV, then you get something that's more asymmetric. So if you take a look in the bottom right, you can see that the dust, which is on the left, the dust flow velocity is a little bit larger than the dawn flow velocity there. And then that also shifts your tail a little bit more towards the dawn side, or the dust side, I mean. All right, so if you take a look at what does this look like in terms of observation? Is it validated with observation? And so in the top left here, in the left side, is the observed velocity in the XY plane. And this is a statistical observation. And if you take a look at the line plot, you can see that the x-axis for the line plot is the magnetic local time, with the dust being on the left and the dawn on the right. And then you can see the observed velocity occurrence is on the y-axis there. And you can see you have a lot more velocity occurrence on the left side. You see a lot more velocity flows on the left side, which is on the dust side. And if you compare that to what we see in the bottom right plots, which is from simulation, the left plot for the bottom right is the uniform conductance case, and you can see it's very symmetric in the tail, and that doesn't match what's being observed. However, if you take a look at what's in the non-uniform conductance case, then you can see that we do get this enhanced flow velocity over on the dust side. So you really need that non-uniform EUV conductance when you're taking a look, when you're modeling or just doing anything with your conductance. All right, so how do we really do this in model? So if you take a look at this plot here, this plot is taken from Korth et al. 2014. There's a lot going on with this plot. So the underlying color is the electron energy flux, which is the precipitation going into the ionosphere. The red contour is the field line current contour, and then the white contour is the upward contour for the upward field line currents, and then the white gray contour is the downward field line current contour. So over on the left, over on the dust side, which is on the left, that's the monoenergetic precipitation. That's the monoenergetic precipitation, and you can see that's very nicely contained within the field line currents, within the region 1 upward field line current. So the monoenergetics seem to be contained pretty well and seem to correlate pretty well with the field line currents. However, if you take a look at the dawn side, which is on the right there, you can see that the diffuse precipitation overlaps with the upward field line currents, but they're not contained inside. They're not contained inside. At the same time, while they do overlap, you can see that there's a lot of fuzziness on the boundary there, and the boundaries don't seem to overlap or correlate very well. So how exactly do we model this? What's actually controlling of these things? So we really need to take a look at the physics, at what's controlling these different populations for precipitation, because precipitation matters a lot. When it gets into the ionosphere, it produces conductance that's a lot more transient than your EUV or constant conductance. All right, so the different types of precipitation taken from Newell et al. 2009 here, which is a statistical analysis of DMSP, you have your monoenergetic precipitation. And monoenergetic precipitation mainly affects the E region, and that's when you have an electron that has been accelerated due to the potential drop across along a field line. And usually these are associated with a field line current. So you have a very strong field line current, then you'll get a very large potential drop. These will accelerate your electrons, and then as a result, you get very high energy precipitation, very high energy electron precipitation. So that's essentially the monoenergetics. And so that's why they correlate really well with the field line current boundary, because you need the field line currents to really energize them. If we take a look at the diffuse precipitation, which is the on the right here, top right here, the diffuse precipitation isn't necessarily, the reason why it's not necessarily or might not necessarily be correlated with field line currents is because the diffuse precipitation are lower energy electrons that have precipitated into the ionosphere. And these lower energy precipitation or lower energy electrons will drift towards the dawn side, and that gives you your nice auroral arc here, is because they're drifting. And so the drift physics is not necessarily included with it when you're taking a look at field line currents. Field line currents, they're along the field line, but the drift physics will give you some sort of perpendicular motion relative to the field line currents, and that gives you your very spread out diffuse aurora. And so that's partly why they're not entirely correlated with your field line currents. And that also affects the E region physics. And then the other population is the broadband electron. And the broadband electrons is a lot softer. They're typically on the order of about 500 eV or so, while monoenergetic is on the order of tens of keV, while diffuse is on the order of about 1 to 10 keV. And so the broadband it's a lot softer in energy. So when they enter the ionosphere, or when they enter the ionosphere thermosphere, they typically deposit most of their energy in the F region, and they don't really affect the conductance that much because it's the top side F region. All right, so how exactly do we include all of these things within a model? And so when you specify conductance, typically you can specify, like an MHD model will typically specify the conductance using like the Moen and Breck relationship for EUV, and that's kind of what you see in the top right here. And then in order to take the precipitation and convert that into conductance, you also use the very famous Robinson formula, which is in 1987. And so you can see that specifying conductance for the MHD, the work's quite old. The other thing you can do is you can couple it to an ionosphere thermosphere model in which you include a lot of the dynamics of the ionosphere and thermosphere. In order to get the conductance out, you have to integrate the conductivity, and then you get conductance. But to get conductivity, that's a really big, complex chain of interactions to get your conductivity. And so on the bottom right here is it's an example from an ionosphere thermosphere model. And you can see that the gradient is tilted at an angle. The location of the sun relative to the magnetic dipole is tilted at an angle. So you get a UT dependence that you don't typically get with an empirically specified EUV. On top of that, you get a lot more realistic response to the different precipitation, different precipitations going in. And so that's kind of what you get in the bottom right here. And I apologize for the rainbow. You know, old papers, they really love the rainbows. You'll see that a lot here. All right, so as far as coupling to the ionosphere and thermosphere, we haven't done a whole lot since then. In 2001 and 2004, using at the time an older version of OpenGGCM, they coupled to CTIM, and what they did was they looked at the electrodynamic response and ionospheric response of this coupling. Essentially what they did was they passed between the MHD model and the IT model, they would pass the conductance and electrodynamics back and forth. In 2004, between LFM and TING, which is the version of the model prior to TIE GCM, they did something very similar where most of the electrodynamics is passed and forth between conductance, field line currents, conductance, and the potentials. What they found was that things, look a little bit better, but as far as the magnetosphere, not too much changed. Things look a little bit better in the magnetosphere. Things look a whole lot better in the ionosphere, but the coupling itself didn't seem to do a whole lot at the time. In 2003, using Batsares and Time GCM, they didn't couple the conductance in this case. What they coupled was the neutral wind generated field line current. So the neutral winds in the thermosphere could contribute some sort of field line currents to the field line current system. So that would be the I and the Ohm's law there, as opposed to modifying the conductance. And what they saw was that there was only about a 6% increase in the polar cap potential. And so since then, no one's really looked at this anymore. There's been quite a gap in terms of improving the coupling. This is kind of the most that we've done in terms of the electrodynamics. So the other pathway that we have is the mass coupling pathway. So what do you do with the mass coupling pathway? So in the mass coupling pathway, you have ionospheric outflow. So from the ionosphere, you can get H plus coming out, He plus, O plus, all these things come out. And then how they come out and why they come out it's quite complex. So ions from the ionosphere, they need to be sufficiently energized in order to escape the gravity. So the heavier the ions need a lot more energy to get them out. And then so usually H plus and O plus ions are accelerated through very different mechanisms. And so for the O plus, you need electromagnetic energy going in. You also need some sort of particle energy like precipitation going in to turn them into ions and then to accelerate them out. All right, so the mass coupling between the magnetosphere and ionosphere, have been looked at quite extensively. So this is a very big diagram here with a lot of citations. And so if you have ion outflow, once they got out, it's easy once they got out, but tracking how they get out, it's a whole nother story. But so they can impact the ring current. The ring current affects the inner magnetosphere, and then that affects the side reconnection. You can have outflow, which affects the magnetopause shape, and that affects the side reconnection. You can get outflow affecting precipitation, which eventually affects the reconnection. And then they also affect the magnetotail dynamics, which also affects reconnection. One thing that was brought into question was how they affect dayside mass loading. The mass loading question, well, let's talk a little bit closer. Let's dive more deeply into how it affects mass loading. So typically for mass loading, you take a look at the reconnection, the local reconnection rate, and that's typically given by this Kasich-Shea formula here. And then the bottom is from a numerical experiment in which you increase the amount of mass that's getting into the magnetosphere. As you increase the mass going into the magnetosphere, you start. So at first, when you give it some mass, you don't really affect the global dynamics. You don't really affect the global reconnection at all. Once you give it enough mass, then you really start to affect the local dynamics starts to impact the entire global dynamics. And that's when you start getting large scale changes in the reconnection potential. And so the interesting thing about this is that with O plus is relatively heavy. So it's really easy if you have a lot of O plus coming in to quickly jump into that local control regime. And so that becomes a bit more important. Why does it impact the global scale? So if this is a plot of the magnetopause and bow shock in the magnetosheath. And so on the left, m equals 0 is when you have not a whole lot of mass coming in, or actually no mass coming in from outflow. And then you increase the amount of mass going up to about 128 protons going in. And so when you have 128 AMUs going in, you can see that the magnetopause has started to inflate a little bit. And then a lot of that mass has escaped down to the magnetosheath, which affects the magnetosheath dynamics. And since you affect the magnetosheath, that then couples back, that then changes your solar wind magnetosphere dynamics and changes your geoeffective length, giving you some changes to your dayside reconnection rate. And so you can see on the right side here is a comparison between the red line is when you have a lot of mass, and then the green line is when you don't have as much mass going in. All right, so how do we really model outflow? So a long time ago, the first thing that happened was this Wingley outflow boundary, which is essentially something very similar to what Batz-Russ does now. You give it a very constant density on the inner boundary, and then electrodynamics, centrifugal force, and acceleration will start pulling a lot of these things out of your boundary. So you get this, you can just start, the forces will pull in the necessary amount of mass that you need into your system. And they found that, getting H plus and O plus going into their magnetosphere model seems to, change a lot of things. Something else that Wiltberger has done was to take a look at, well, instead of just letting the dynamics pull mass, a whole bunch of mass in everywhere, how about we just specify little patches of mass going in? And so what he did here was he put a little, it's hard to see, but it's like little yellow squares at the cusp on the left there. He put mass specifically outflow going out specifically at those cusp locations to see what really happens to the magnetosphere as a whole. And what he found was that when you have outflow going in, you start getting, the onset of the storm, you could get a second soapstorm that's very O plus rich due to this amount of mass coming in. If the outflow rate is a bit too fast, then you don't really get the second soapstorm. If it's too slow, then you don't really get it. You need to get the outflow just right to really get that second soapstorm. Other things that have been done is taking a look at empirical outflow modeling. So you can try to use some sort of empirical relationship between outflow and AC pointing flux or DC pointing flux, which is what this is trying to do, is trying to extract your pointing flux, your AC pointing flux and DC pointing flux. And how you get the pointing flux is also quite difficult to get at, especially in an MHD model. It's typically the timescales that are difficult to extract. And so with AC and with this empirical specification, they found that, well, you can get a lot of substorms. You get them in the right places with the right amount of outflow rate and velocity, and it seems to impact the magnetosphere quite a lot. Let's see if I can start these videos. So if you don't really have a whole lot of outflow, then you kind of get into what's a SMC steady, your steady magnetosphere convection state here, which is on the left. And you can see that it's relatively regular, not a whole lot is changing, it's pretty steady. However, if you have a lot of outflow coming out, which is on the right there, you can get these sawtooth-like substorms or sawtooth-like events, which is very periodic and very large disruptive substorms coming in. See if we can see one pretty quickly here. All right, there you go. You see a really big substorm just launched on the right plot there, and that would be your typical sawtooth substorm. They're quite disruptive. All right, so rather than using empirical specification, we've kind of upgraded things since then, and we have outflow models now. So you have the Pham, which is the polar wind outflow model, and then you also have the IPWM, which is the ionosphere polar wind model. So on the left is a coupling between Pham and SWMF, and using that coupling, they found that during storms, including ionospheric H+, they reduce the root mean square error of simulated GOES magnetic fields by 50%. That's a pretty significant amount. And then on the right, using the IPWM coupled to MF-LFM, what they found was that, well, if you try to use some sort of integrated rate like total ionospheric outflow, it doesn't mean anything. What really matters is the amount of ions coming out and how the ions got there. What's the velocity of the ions, the energy of the ions, and really how they get into the magnetosphere. Not so much the amount of ions coming out. You really need to know, exactly where they're going and what's happening. So one thing that's tried is, let's attach the thermosphere in there to allow the thermosphere to really control the mass rather than just, so in this figure here on the left, you can see that, well, on the left, you can see on the bottom right is the upper atmosphere, and that's coupled to Pham. Typically for the upper atmosphere, you will couple something like MSIS, which is an empirical thermosphere, or you can use an actual ionosphere thermosphere model. On the right side, it's not shown, but the right side was also using MSIS at the time. So what we did was we coupled the ionosphere thermosphere model to IPWM. And so now you have the thermosphere being involved, and the thermosphere can also change as a result of this coupling. And so in order to examine the mass coupling, we removed the electrodynamic coupling, and then we looked at two different thermospheres. So we have a solar minimum thermosphere and a solar maximum thermosphere. So obviously, when you change the thermosphere, you get very different amounts of outflow coming out. With the solar maximum thermosphere, you get a lot of mass coming out, and then as a result, you do reduce the reconnection potential. With the solar minimum, you don't get as much mass coming out, so you don't really affect the reconnection potential. So the right figure here is the magnetosphere, the magnetospheric states for solar minimum at the top, solar maximum in the middle, and then a comparison of the magnetopause boundary on the bottom. And so the white lines is the magnetopause boundary given as like a BZ equals 0, which is a very quick and dirty way to get your magnetopause boundary. And that only really works if you don't really have any sort of north-south asymmetry. So one thing to note here is that it's just perfectly symmetric ionosphere thermosphere. You have the same outflow coming out to the north and the same outflow coming out to the southern hemisphere. And so when you have a whole lot of mass coming out, the mass seems to load the magnetosphere, especially in the magnetotail, and then it gives you a very symmetric magnetotail. When you don't have as much mass coming out, if you remember when we were talking about the electrodynamic coupling before, when you have that Hall gradient in the conductance, you get a very symmetric tail. And so when you don't have that much mass coming out, you maintain your tail, your symmetric or your anti-symmetric tail. You get this very Dundas asymmetric tail. And so when you have a whole lot of mass coming out, you kind of load the whole magnetosphere equally on both sides. It distributes the mass and the mass takes over. And so you get this much more symmetric tail coming in when you have a whole lot of mass being loaded. Other things that were looked at is, oops, what happened here? That plot just went away. All right. Anyways, there's supposed to be another plot on the left, but you can see that that quickly went away. And what that was supposed to be was an SWMF, simulation of what happens if you have an anti-symmetric, when you have an asymmetric outflow. You have a different outflow going out to the northern hemisphere and a different outflow coming out for the southern hemisphere. And so when you have different amounts of outflow coming out between the northern and southern hemispheres, you load your magnetosphere very differently, and that changes the direction of your tail. So your tail starts to become more symmetric when you have, not more symmetric, you get a very asymmetric tail when that happens. And so when you compare that to cluster, which is the results on the right, you can see that when you take a look at the gray line, when you take a look at the gray line, you can see that the gray line completely misses the blue line, which is the observation. However, when you do include asymmetric outflow, then you more closely match what cluster is observing. And cluster in this case is kind of flying through from the northern hemisphere to the southern hemisphere. So it's in a pretty good location to really observe the north-south asymmetry. And so you really need to include some sort of asymmetric outflow rather than symmetric outflow, like some of the other empirical specifications and models we're doing. All right, so let's kind of go back to that electrodynamic feedback loop. That's all the latest results from coupling to the mass coupling and ionospheric coupling. Let's kind of take a quick, let's take a trip back to the electrodynamic feedback loop here. So I put that into these three separate circles. If you have a more realistic conductance, you get a more realistic magnetosphere. If you have a more realistic magnetosphere, in turn, you get a more realistic high latitude input like precipitation and potential. And then that goes into some sort of ionospheric, thermospheric model, and that gives you more realistic conductance in return. So you really need that coupling. If you don't have that coupling and you're trying to specify your conductance empirically, you break this loop and you don't improve your model. If you start the model anywhere, it doesn't matter where you start, as long as you have this coupling embedded in your model, you improve everything as a whole. IT models typically use something like a Weimer empirical specification. That is not, it's pretty good, but it doesn't do that well when you have very dynamic driving and you need more dynamic precipitation and things like that. So let's take a quick look at how that this coupling feedback loop really works out. So using the multi-scale atmosphere geospace environment, or the MAGE model, which couples TiGCM to some sort of ionospheric electrodynamics model, which is the remix model, coupled to Gamera for the global MHD, and then coupled to the ring current, the Rice convection model of the ring current. So this is all coupled together, and then since this includes a ring current, it's pretty good for examining geomagnetic storms. And we did this at high resolution, which they didn't do, way back in 2001. In 2001, the IT models had a resolution of, 5 to 7 degrees in latitude and longitude. Now we're looking at about half a degree everywhere. And then your central plasma sheet is looking at about, 300 kilometers or so, as opposed to 1,000 or more kilometers way back. And so we've really increased the resolution of our model. And let's take a quick look about, what that really does. And so what you see here is the neutral density within the ionosphere thermosphere. And then you see two satellites that's flying through. You see the CHAMP satellite track, and then you see the GRACE satellite track. And the bottom is the neutral density as a function of time. And you can see this thing moving forward as this movie plays. And the black line is the CHAMP and GRACE measurement, the observed neutral density from CHAMP and GRACE. And then the blue and red line is the MAGE results, the simulated neutral density. So the interesting thing about this one is typically when you talk about and compare neutral density, what they've done before is they would look at things like daily averages or orbit averages or some sort of large scale, temporal average. Look at this. We get pretty good, we get a pretty good agreement looking at this on a 1 minute cadence. So we're comparing it, on a 1 minute time scale, and we get pretty good agreement throughout, between quiet period through the main phase of the storm, and then going through towards the recovery phase at the very end here. So let me skip forward a little bit, and you can see a lot of waves in the neutral density coming out. And that's going to be important, because when you have something that's only like 5 or 7 degrees, 2 decades ago, if you have something that's 5 or 7 degrees, you can't really maintain and propagate these waves coming out. So these mesoscale structures are very important, and you really need the resolution that we have now and the capability that we have now to really capture a lot of these small scale structures. All right, so if we take a look at the root mean square error and the R squared, and we distribute the entire plot that you just saw in terms of latitude to take a look at, how well we perform compared to Weimer, which is what the IT community likes to use, Weimer or Helix or something like that. And so this goes from the high latitude in the southern hemisphere on the very left, which is between -9 degrees to minus 60 degrees latitude to the mid latitude, and then you have the equatorial latitudes, and then you get the northern hemispheres on the right there. And if you take a look at the root mean square error, we have lower error than Weimer, which MAGE results are in the gray and yellow, Weimer's in the blue and orange. And you can see in the root mean square error, we do a lot better with MAGE, just pretty much across the board. But you can see that we have a lot lower error in the equatorial regions, which is the two middle plots there. If you take a look at the R squared, you can see that we have a significantly better R squared in the lower latitudes, even though in the IT model, we're only inputting the magnetospheric driving at the high latitude. So what's really going on here? What this is saying is that we get the large scale global features, the global input of energy into the IT model pretty well. And so when those large scale inputs propagate to the equatorial region, we do a good job. However, when you look at the northern, the high latitudes, that's dominated by a lot of really small mesoscale features, and we're still missing a lot of those. We get some of those right, like large scale ones and some of the larger scale, medium scale ones, we get some of those right, but we still need to improve our specification, especially the mesoscale structures in the high latitudes here. All right, so let's quickly review the pathways here. So I added the ion outflow to that feedback loop that we had earlier. I added the ion outflow to the right. So you start with, we can start anywhere. Let's start with the magnetosphere. You start with the magnetosphere, you input that magnetospheric energy into the high latitude. And what that does is that either impacts the conductance at the top here or the ion outflow. And then both of those would feed back into the magnetosphere and then change the magnetosphere. So just including these loops within your modeling or within your analysis, including these loops kind of improve everything. You need to understand all of these feedback loops, and enabling these loops also improve your model. So they're very important in capturing mesoscale features. They're really important to resolve and propagate mesoscale features. But we weren't able to resolve a lot of these before because all of our models are really coarse and not doing a good job. All right, so in addition to just capturing the mesoscale features, other important things is coupling across the different domains. So for example, you have multi-scale ring current buildup, you have small scale structures, along with BBFs and larger scale structures. And then a lot of that will map in, and then you get mesoscale structures within the ionosphere, like TOIs, SED plumes, polar cap patches. I guess SED plumes aren't that small scale, but you get a lot of like TOIs, tongue of ionizations, which is this region in the middle that's going from the SED plume into the polar cap. And then you have patches and then other features like STAPs and so on. And then there's also lower atmospheric ionosphere coupling, which has a lot of mesoscale features as well. We need to start including a lot of that coupling. So, on the right side, on the top of the right side, is SAMI3 coupled to just a simple empirical thermosphere. And you can see it's very smooth and large scale structures. However, when it's coupled to a more dynamic ionosphere thermosphere model like WACOM-X, you can see you get a lot of these little bubbles that are there. These bubbles and ripples start to show up. So you really need to couple into more dynamic models and not rely on large scale empirical specification. All right, so going back to the title, which talks about thermospheric dynamics, how does the thermosphere affect everything? So solar ionization is kind of the main culprit of how the thermosphere impacts things. So you have solar ionization comes in, it hits the neutrals in the thermosphere, they become ions, and you have energy in the electrons, and that starts to impact the ionosphere. That changes your conductivity, that changes conductance, and then that goes back into everything. So features that were really important in the thermosphere, with a coupled model and starting to couple everything and all the different domains together, they start to become really important to all of geospace, not just the magnetosphere, not just the thermosphere. These features start coupling and they start crossing these boundaries, and by getting them all together, it starts to become really important. So one thing is a solar flare. Typically in the magnetosphere, you don't care a whole lot if there was a solar flare or not. You only care if that CME is going to hit us. But now you might, so Liu et al. Here in 2021, it's a Nature paper. They used the LFM, TiGCM, RCM coupled model to take a look at what happens when you have a solar flare coming in. So the solar flare changes the EUV it changes the ionization rate that's going into the thermosphere. And so they simulated a storm with and without the flare. So what you see on the right here is you have the left column on the right, A, B, and C are all from the flare event. And then you have the observed TEC from GPS satellites, and then you have no flare on the right. So you can see that if you compare the no flare, well, since it has no flare, the difference between with and without the flare, the top row is before the solar flare, the middle row is at the peak of the solar flare, and then the difference between them is in the bottom row. So without a flare, it doesn't matter if you're looking at the peak of the flare or before the flare. Without a flare, it doesn't really make a difference. And so everything is quite zero in the bottom right there. The whole no flare run just doesn't see anything. if you include the solar flare as part of your calculation, you can see that we match pretty well with what GPS sees. And so you can see at the pre-flare, we get a little bit better. This has to do with slightly different specifications, slightly different models on how they convert from solar EUV into solar ionization and so on. And then the middle row, which is the flare peak, you can see that with this enhancement in the EUV gradient here, you can see this enhancement in the ionization, we match what GPS is seeing. So you really need that solar flare and EUV from the solar flare you really need to include that in your model. And you can see there's a very large difference in the bottom right. So what does that do to the magnetosphere? If you take a look at the polar cap potential, which is on the left here, the black line is the no flare line. And you can see that there's relatively no difference throughout this event. And you can see it sits at about 100 kilovolts the entire time. If you include a solar flare, which happens near 12 UT here, if you include that solar flare, you see this really big drop in the polar cap potential. And that has to do, if you at the start of this talk, the increasing your Pedersen conductance decreases your polar cap potential, and this is essentially the result of that. So it's just a really simple Ohm's law. You increase your conductance everywhere due to this solar flare, and that just gives you this big drop in polar cap potential. And then the bottom left, that's your Joule heating, and you can also see as a result, since you reduce your polar cap potential, you're also reducing your heating. All right, so how does that affect the structure of the magnetosphere? So the left again is the flare run, the middle is the no flare, and the right is the difference between them. So since your flare comes in and gives you this really big EUV gradient coming in, that very large scale change in the EUV gradient gives you a large scale change in the symmetry in your tail. And so you can see with the large gradient, you get a lot more asymmetry in your magnetotail in the flare run with a velocity enhancement on the left. However, if you look at the no flare run, it's a pretty symmetric tail. Your flow velocities aren't doing, they're kind of equal on both the dawn and dusk side, and you don't see much of a difference. So, and if you take a look at the difference plot, you can see Themis A and Themis C are at the bow shock, and this paper does do a comparison and show that Themis A and Themis B do see a compression of the bow shock. And that's exactly what, we simulated a small compression of the bow shock. Themis also sees a compression of the bow shock due to the solar flare. So you kind of need a solar flare, when you're doing whole geospace simulations and just looking at your analysis, you really need to include solar flares now, apparently. Other things that the thermosphere, ionosphere community has looked at for a long time are solar eclipses. We haven't really considered solar eclipses in the magnetosphere. So in Chen et al. 2021 here, they simulated the June 2021 solar near total. I think it's like 95% as opposed to 100% totality. So it gets really close to totality, but it's not quite a total solar eclipse. And they took a look at what happens when you have a solar eclipse. So the right plot is TEC again, but the top panel is TEC. The middle panel is your Pedersen conductance, and the bottom is your energy flux, which is precipitating electrons. And so the left column is the simulation with the solar eclipse, and then the right plot is the difference between a simulation with and without a solar eclipse. And then you can see the eclipse factor in the bottom right, so you can get a sense for when the eclipse is occurring. So let me play this movie. So as we get close to the eclipse and as the eclipse starts happening, you can see when the moon blocks the sun, that starts covering the solar EV, the amount of solar EV able to get to the ionosphere. And so as a result, you get this conductance hole that starts moving across the polar cap as a result of the moon moving across and covering the sun. And so you can see this very large scale change in the Pedersen conductance here moving across, and you can see it's this big circle. And as opposed to the solar flare, which is more like a punch, because that just hits us really quickly and then goes away, a solar eclipse is really gradual and it slowly moves all the way across. And so on the left plot here, all the line plots here is a comparison between the difference between with and without the solar eclipse. So you can see that there are some differences in not just the northern hemisphere where the solar eclipse is happening, but you also see some differences in both the northern and southern hemisphere. So this was just a really early and quick results. We're still examining, we're still looking for what's really happening and what the solar eclipse is doing. This is just initial analysis for this, and work on this is still ongoing. All right, so kind of to wrap things up, so some final thoughts and then some future challenges. This is not necessarily an extensive list to MI coupling, but we really need to take a closer look at self-consistent modeling to improve the self-consistent modeling rather than using empirical specification, because you start enabling a lot of these feedback loops that are really important, and you just improve your whole model. You need more physical precipitation, Hall MHD, there's a lot of things like that you can include. We also need to revisit things that have been kind of put on the back burner or just stop being considered, like neutral winds, like that coupling with the ionosphere thermosphere coupling before was, rather than just 6%. Now that we have all these mesoscale structures and all of these, significantly better models that we can, before they didn't really have a ring current model, so you couldn't really simulate the storm that well. Now we have ring current models coupled in. That gives you much bigger storms. That gives you much better storms and better specification for high latitude. So we really need to revisit a lot of the old coupling ideas and try to see, are they really as insignificant as we thought them to be? We also need to start covering these transition region physics like BBFs. BBFs coming in, they start, they're kind of in between the different things, the different domains, like they're really fast flows that penetrate really deeply into the inner magnetosphere. And so and then how do they map to the ionosphere? Are they related to, how much are they related to omega bands, and how, what do they really do? And then other things is you take a look at like exosphere. We don't really have a good exosphere model. That's just, we jump from the inner boundary of an MHD model, and then we typically go all the way down to 100 kilometers. There's this big region that's like almost one RE in size that we're completely skipping. So we really need something like an exosphere model, or models that really bridge a lot of these transition regions. And then we now need to start looking at the whole magnetosphere kind of sideways. Before, what we did in terms of, the mass outflow is we looked at the polar cap. We would do, we have ionospheric model like Pham and IPWM, which focus a lot on what happens at the polar cap and the polar winds and the ions coming out and energized to the polar regions. But we also need to look at, okay, what happens when the ions from the ionosphere thermosphere exit near the low latitudes and equatorial region? They exit into the plasmasphere, refill the plasmasphere, which, and then they also exit into the ring current and help with the ring current. And then that in turn can couple back into, not back into, but it will couple into the MHD and flow within the MHD domain as colder populations that, to be energized, because you need some sort of sea population to really do a lot of this. And so, this is not an extensive list. It's just, some challenges that I was able to come up with. So feel free to think up your own and add to this list. And then as a last thing is, for the students and postdocs out there, the Center for Geospace Storms is hiring. All right, thank you.
First, that was a great talk, Kevin. I really appreciated all your points and how exciting it is that you guys are like melding the different models. This is exactly what GEM is for. So congratulations. I also especially loved you pointing out how important it is to include mesoscale physics. I think that's, what we're all seeing across the different regimes, how important that is. And in the CDAR community, I've been working with some groups like Yue Deng, who uses the GITM model. And like you, they're also realizing, we really need to include mesoscale physics. And now the models can actually capture that physics. So one way that we're addressing it, or they're addressing it, is using data as an input to essentially specify what are the mesoscale precipitation or plasma flows using, say, the all sky imagers or SuperDARN and stuff like that. So I'm just curious, for what you're doing, have you guys considered using data as a direct specification to capture those scale sizes, or are you primarily using the coupled models, like relying on, say, the magnetotail physics to specify the mesoscales in the ionosphere?
Well, that's a really good question. with the different, with data, it's hard to really understand what the physics are driving data. But the nice thing about it is you don't need to understand the physics of driving the data. So that, that is important, and that's something that we've considered doing. But at the same time, it's also nice to really take a step back and try to understand what are the physics going into this, so that we can use that for the future. Because what happens if you don't have the data? Like, for example, Van Allen probes are no longer there. So if we want to do something like the 2021 or 2022 storm, we don't have that data anymore. So we really, should try to understand and try to understand what the data is telling us, and then using that to get a better understanding of everything, and improve both the model, and the data, and get, identify where we need data.
Mhm.
So I think we kind of need to do everything.
Great, thank you.
Any more questions? Yeah.
Yes, I have one question. Yeah, I enjoy your talk very much. That's great. You mentioned that the importance of an exosphere. Are you suggesting? I suggest that the GEM community to push for next mission to the measurement of an exosphere up to maybe moon altitude, latitude.
Well, it looks like Hyunju has a comment.
Very good question. Yes, exosphere, I think we've been ignoring a lot, but there's a start discovering from the twins Lyman Alpha observation that the exosphere is no longer steady. So you guys talk about the Lincoln scientists, you guys talk about the charge exchange is one of the major loss mechanism of ring current energy. And exospheric density is changing during the storm time as well, everyone. So you have to consider that no longer static exosphere model should be there. And also to answer the Yongliang's question that there's a glide mission that goes to the Lagrangian 1 point and then looking back to the Earth and then taking the Lyman Alpha observation and see how those glow changes, so geocorona changes. And another one that I've been writing proposal, and that is about the in situ measurement of the hydrogens in the along the geosynchronous transport orbit. Thank you.
Sorry, I have another comment on yeah, because hydrogen is very important, and but also we should not ignore the atomic oxygen, because the hot atomic oxygen also fly out into the geospace and play important role because the mass, right? Mass is important, mass flow, that Kevin is mentioning that. So I think both hydrogen and atomic oxygen, both of them are important. We need to make measure those kind of things together.
Thank you. And I would like to say the technology may not be really advanced enough to catch the low density. Do you know how low it is? It's very tough.
Yeah, just okay. So sorry, just one quick comment, because I'm working on the timed groovy data. We measured Lyman Alpha atomic oxygen emission. Recently, I found that we can use 1304 to measure atomic oxygen density up to 500, 600 kilometers. We still have a very strong signal there. I think it's possible we can extend to a few thousand kilometers, even moon orbit.
Let's talk together.
So last comment on that is that it's not just something that I'm advocating for the GEM community. It's something that bridges the GEM and CEDAR community together. It's something that we all need to do.
Hey, Kevin, nice talk. And, on your slide about future directions, you're talking about, neutral winds and exosphere. And, Hyunju just pointed out that GLIDE is going to be flying soon. And I'll just add to that it's going to be providing 3D density retrievals every 30 minutes, continuously. So that I think will be a real resource on that. And GDC is going to be providing neutral wind measurements together with the incoming, precipitation and whatnot, which I think will help with the neutral wind. So I'm curious though, if those two things are going to have new measurements coming up to support us, what do you think the next mission should be, that would support other, open aspects of MI coupling? Is it something on outflow? Is it something on the electron dynamics? What would you think?
Oh, that's a good question. I honestly not sure. There's just so many things we're not even sure. Once those missions come out, it will be a big breakthrough, and we might figure out there's a lot more physics that we need to include and look at. And I think there's a lot more missions and a lot of things that I really need to revisit and look at. And I think outflow and electrons we're missing a lot of data from those now, so we might need those.
All right, thank you.
Thank you very much. So our next speakers will be joining us online, and I would like to invite our students to introduce them. Grant Berland and Espen Frederick.
David, if you'd like to share your screen and load up your slides.
Yep, we'll do that. Hold on one sec and share here. Share.
While you're getting that set up, you can be introduced.
Yeah. Does everybody see the right one, not the presenter mode?
Yes. I don't know if you can hear me, but you're looking good.
Yep, I can. Yep.
Cool. Just bear with me for this too, because we have 3 speakers in one session. And I think there's going to be like 2 presentations. So David and Caroline are going to do their first one. And then Claire, I think, is going to go after that. So I'm going to introduce them all at once here. And then I suppose when it's Claire's turn, I'm just going to kind of be like, right, it's time to go. So hi, I'm Espen Frederick. I'm a graduate student at the University of Texas at Arlington. And I'm here this morning to introduce our DEI speakers. So as many of you know, for decades, the Hawaiian Islands have been the site of world-class astrophysical and solar research. However, this work is often done without input from Hawaii's local residents and especially Indigenous Hawaiians. So our speakers today are just a few of many who are hard at work attempting to bridge that gap and fostering authentic community engagement and outreach throughout Hawaii. So today in the first talk, Dr. David Boboltz and Caroline Blanco are going to be speaking on their mission of driving NSF community engagement in Hawaii. And then we're going to have a follow-up after that with Dr. Claire Raftery. So Caroline Blanco received her Juris Doctorate from the Washington College of Law, as well as a BA in American Cultural History from Northwestern University. She currently serves as Assistant General Counsel for the National Science Foundation, providing legal counsel on environmental and cultural resources. Caroline furthermore serves as Federal Preservation Officer, the NSF Tribal Liaison, and is the chairperson for the NSF's Committee on Environmental Matters, which works with members of the public as well as Indigenous Hawaiians here. Dr. David Boboltz received his PhD from astrophysics at Virginia Tech, in addition to receiving a master's in applied physics from JHU and a bachelor's in mechanical engineering from Virginia Tech. He currently holds the distinction of program director for the NSF's Division of Astronomical Sciences, which manages the National Solar Observatory nearby, and includes the Daniel K. Inouye Telescope, which is on Maui. So he brings to his career experience from his work in a wide variety of fields, including his time as a radio astronomer for the United States Naval Observatory. And then finally, for the second talk after this, a culturally conscious science educator, Dr. Claire Raftery, received her PhD in solar astrophysics from Trinity College Dublin in 2010, and is currently pursuing a master's in higher education in order to further her work in science education outreach. She currently holds a distinction as Head of Education, Outreach, and Communication at the NSF's National Solar Observatory as well. So for our first talk, please join me in giving a warm welcome to Caroline Blanco and Dr. David Boboltz.
Okay, well, thank you so much. That was for the kind introduction. And so we're going to talk about a little bit about some of the work that NSF's been doing over the past 10 to 15 years, talking about basically trying to build new facilities in the Hawaiian Islands. And so, and some of the engagement we've been doing with the local community for those big construction projects. So the talk, For Caroline and my talk, we're going to concentrate on two projects. One is the Daniel K. Inouye Solar Telescope, which recently came online. And then the second part of the talk, we'll talk about some of the future projects that the NSF may be interested in moving forward with. So here's the Daniel K. Inouye Solar Telescope. It's been a long road from the site survey, which began in 2001, through various permutations about permitting and litigation, through the groundbreaking. We actually broke ground for site construction in December of 2012. We constructed the telescope for almost 10 years, and it began science operations late last year in December of 2021. And I've been the program director for the Daniel K. Inouye Solar Telescope construction for about 9 years since I joined NSF, and I've worked with Caroline for most of that time. So a little bit about some of the complexities involved in building one of these big projects. Not only do you have the engineering complexities of the telescope itself, but you also have a lot of different interplays between regulations and permitting, especially on a site such as on Haleakala on the island of Maui. And so here you can see on the left, I have a diagram of what the site looks like. The site itself is owned by and managed by the University of Hawaii. And it has several federal agencies that have equipment there on the site. So you can see here the Air Force has their Maui Space Surveillance Complex. The Department of Energy has a small facility. The Federal Aviation Administration has a facility there. And then the National Science Foundation was interested in building DKIST here on the site, in addition to the observatories that are operated by the University of Hawaii itself. This plot of land that the university owns is within state conservation land, which is overseen by the Department of Land and Natural Resources. And then within that is in the much larger National Park Service, Haleakala National Park. And so you can see there's a real complexity in trying to construct a DKIST on this site. So I'm going to turn it over to Caroline to talk a little bit about some of the legal authorities.
Thanks, Dave. And hi, everyone. It's nice to be here. My main area of practice is in environmental law. And so that's why I became involved with this project, environmental, and that includes cultural resources law as well. So whenever a federal agency gets involved in a project like this, or a proposed project, and in our case, it would be funding a project, we have to consider the environmental impacts associated with that project, and also impacts on historic preservation, impacts on endangered species, and so forth. So this slide takes a look at that, and it's a process. These processes don't mandate a particular outcome. They definitely just go forward and involve the public. These are our processes, especially the first two, the National Environmental Policy Act, NEPA. This is where you may have heard about draft environmental impact statements and so forth, and public comments on them. In this case, because we were going through a national park, and there was a park road, and it was an historic park road, we decided to, and this is when I came on board at NSF, I looked at it and said, we really have to go back out to the public and do a supplemental draft environmental impact statement, because we had to look at the consequences of going through the park. So we went ahead and did that. In this case, we then did a final EIS and then ended with a record of decision. The more complicated ones were really the National Historic Preservation Act, which we'll go into a little more detail with. And what's in particular, it's called Section 106. It's a consultation process. It ended in an agreement document called the Programmatic Agreement. But this particular statute deals with impacts on nationally significant historic resources. They can be archaeological, they can be historic, they can be cultural. And so in this case, we looked at the mountain itself as being of cultural significance to Native Hawaiians. And so we took a look at that, and then when there are significant and adverse effects, which we did determine that there were, then we work with interested parties that we call consulting parties on ways in which to avoid, minimize, and or mitigate those adverse effects. And the outcome of that consultation process is what we called was a programmatic agreement. And that's what the statute provides for, and that's what we did there. There were also some endangered species processes that we worked with, the Endangered Species Act, and also a state process that we dealt with where we came up with a habitat conservation plan that was very, very successful in increasing the population of Hawaiian petrels, the seabirds. Next slide, please. So there, as Dave said, there are a lot of obligations that we have, and we took our obligations very, very seriously. This is just to give you some of the statistics to show the complexity of what we had to deal with, and we gladly took those obligations on. But there were 10 agreements, over 150 obligations, and we completed those obligations. And most of these had to be done before construction. Some could happen concurrently with construction. But some of these, the one on the fourth bullet point there, were actual provisions, or some of them were provisions that were included in the programmatic agreement. And that included something that was pretty novel, and that was the decommissioning of the telescope in 50 years. And that was not something that had been included in a programmatic agreement before. Also, we had telescope time for Native Hawaiian scientists. We looked at periodically looking at different paint so that we could maybe determine whether, a color, instead of white, it could be a different color that might blend in with the landscape better. So there were lots of different things and different obligations, the petrel mortality reporting that we have to continue taking a look at, and other things, rodent control, invasive species control, and so forth. Next slide, please. So this programmatic agreement is probably, for purposes of this discussion at this conference, this is something that was really an important step toward trying to work together with Indigenous people to try to really get it right as much as we possibly could. And it is an evolution. It is something we've tried hard to work at, and we're getting better. We can't say we figured out how to do it exactly, but we are getting better. We're committed to it. And what we did here is we created this programmatic agreement. It's supposed to be in effect for 10 years, and it was supposed to start in December of 2012 when construction started, when everything was all set to begin. And we decided to start it early. We started it actually 3 years early, and we started meeting with what we established, this Native Hawaiian working group. And we thought that it would be helpful to engage with people early on and to talk through the entire process while construction was happening, so that we were being transparent. People knew who we were. We were meeting with them twice a year. They had a say in certain provisions that were set forth in this programmatic agreement, so that they became a part of what was going on. And that was a healthy conversation that we had throughout all of this. We're still meeting today. So we've been meeting since December of 2009. It was not always a very comfortable time when we met with people, but we've all learned a lot through the entire process. It's been a really fascinating experience, I think, for everybody involved. So there are lots of different provisions, and one of the things was, this is sorry, thanks, Dave. But there were a couple of things there, like a cultural monitor that we had coming. We asked them to, in fact, weigh in on the scope of work for the contract that we were going to let for the cultural monitor. And so that was really helpful to see what their perspectives were on that. There was a state road that had very important documentation that needed to be done because it was an historic road. That wasn't so much a Native Hawaiian issue as it was an historic properties issue. But some of the other ones that did deal with the Native Hawaiian Working Group were things like a cultural practitioner shelter, Star Compass, and maybe turning some of the road name. There was one road up at Haleakala High Altitude Observatory, and the discussion was whether it should be changed to a Hawaiian name. And ultimately they decided no, but it was a topic of discussion. And then another, and the most recent one that was actually completed was artwork. So there is a cultural practitioner shelter up there now, and it's been in place for a couple of years, and that's allowed people to have a place to come to. It's got restroom facilities, a place to sit down, get in from out of the elements. If they want to engage in cultural practitioner or they want a cultural practice. And so that's something that people really appreciated that we were able to do. Next slide. A little bit of foreshadowing before.
Oh. Sorry.
That's okay. It was not behaving. There you go. So this was actually, we did meet, this is at one of our meetings, and this was really interesting. This was a star compass, basically, that they, or the navigation, they tried to show us what, how these were the navigators. They came out and they showed us how they dealt with navigation, and it was really fascinating. It was a really wonderful cultural experience, and everybody really thought it was really interesting and helpful. So this was something that, as I said, you know, we had this programmatic agreement allowed for ongoing consultation with members of the Native Hawaiian community and the National Science Foundation and the project team. And so they knew what was going on, and there were no surprises about how things were progressing. And as I said, we continue to meet to this day twice a year. The pandemic hasn't allowed for us to meet in person for a couple of years, unfortunately, but we have maintained at least a virtual presence. And we think that ultimately it was a good outcome.
Sorry.
So no, it's okay, Dave, it's fine. I'm finished with that slide, we can move on. And Dave, have you covered this?
Yeah. I'll talk a little bit about this. So in addition to the requirements that we had in the programmatic agreement, we also wanted to try to go and take a step above and beyond, you know, these obligations and you know, see what we could do to actually benefit the local community that's, you know, allowed us to use their mountain for our science. And so one of those things that that NSF did was to provide this 10-year, $20 million award to the University of Hawaii and Maui College for this program called Kahikina Okala. And the idea is behind the goal of the program was to try to build a bridge between STEM education, which NSF is very focused on, and Native Hawaiian culture, which the community is focused on. And so this program supports students pursuing degrees in any STEM related field. And they also, they have a bridge to the Native Hawaiian Studies program. You can major in either one of them, but the cohort that moves through this program takes classes in both and does both activities. And this cohort of students, they're supported by the university through this grant from NSF, and they at UH Maui College they pursue their associate's degree, but they can move on and pursue additional degrees, still supported by the university, all the way up through their PhD if they choose to do so. And so here's some of the statistics from the recent cohort. And so you can see they have about over 100 participants. Recently they had 34 graduates, and you can see in the blue the distribution of some of those graduates in STEM education. You can see that they range from associates all the way up through, we actually have 2 PhD students. Both of them happen to be in astronomy, although that wasn't a restriction for the program. But we really like to see Native Hawaiian astronomers. So the construction of the telescope wasn't without its difficulties. And so many of you may be aware of this. There's been some issues about constructing telescopes on mountains in Hawaii. One of these issues came up in 2015 when the 30-meter telescope, which is a nighttime telescope project that we're going to talk about in several of the slides to come later. They had been recommended in an early astronomy and astrophysics decadal survey, the 2010 decadal survey. The project does not have NSF funding, but they do have their own private funds, and they have international partners. That project was ready to begin construction in 2015. So they tried to start construction. That construction was halted by protesters on the Big Island of Hawaii. In the meantime, we were in the midst of our construction for DKIST. And so some of those protests happened to spill over to Maui. And so during this time when TMT was starting up construction, we also happened to be doing what we call these extra wide load transports up the summit. And you can see here in the lower right-hand corner an image of that. And so during those transports, we had to close down the National Park Road. We had to provide 30 days notice of this. And so the first time we attempted one of these transports, it was halted. It was, very soon after. You can see it was almost the day of the TMT construction start. And so it was halted by the protesters there. We regrouped, we talked to the Maui police force, and then we attempted our second transport the next month in July. And this transport was successful. We did have to, the Maui police force did have to make a few arrests in order to allow the transport to move through. And then we had a third transport attempt in August, and again had some protests. So after a while, so DKIST was able to continue on with construction without any additional issues. However, TMT, after these initial protests, they decided to put a halt on construction, and they went through several years of litigation. And this ultimately led to a ruling in favor of TMT, and they were allowed to move forward. They got their permit to begin construction, or their permit was validated by the Hawaii Supreme Court. And so they again attempted to start construction in July of 2019. Again, wide-scale protests ensued, whereas for the previous construction start attempt, they had tens of people, both on the Big Island and on Maui for DKIST. Here they had hundreds, if not thousands, of people that gathered together. They started camping out. They completely blocked the road to Mauna Kea. And so TMT, to their credit, decided that they would put a pause on construction and sort of reevaluate where they're going, and perhaps try to move forward a little later. In the meantime, in May of 2020, NSF received planning and design proposals for what's called the US ELT program. So it's the US Extremely Large Telescope Program. And that's a Northern Hemisphere, Southern Hemisphere joint project between TMT, the Giant Magellan Telescope, which will be built in Chile, and then NSF's NOIR lab, which is our nighttime equivalent of the National Solar Observatory. It's our national lab for nighttime OIR astronomy. And so normally we wouldn't say anything about these proposals due to Privacy Act restrictions. However, the two telescope projects decided to publicly acknowledge that they had submitted these telescope proposals. So NSF, once this was acknowledged, and knowing that construction on Hawaii and especially on Mauna Kea is a very sensitive issue with Native Hawaiians, we issued a statement saying that we were planning on conducting what we called an informal outreach effort, which was something very unique for a federal agency, in which we're not even participating in the project yet. And so, we put this out on our website, and we requested that people contact us and to discuss so that we would just listen to the issues with building telescope projects on Mauna Kea, and listens to people's feelings on Mauna Kea. And that led to this community engagement and then in our informal outreach effort that I'm going to let Caroline talk about.
Yeah, thanks, Dave. Yeah, this really is a novel thing that we did. We weren't required to by any law. We just thought it was the right thing to do. We hadn't even decided, and still haven't said we're seriously considering funding TMT. That's usually a trigger when an agency is seriously considering an action. That's when they would begin formal environmental compliance and reach out to the public. But we weren't doing that. We just knew that there was a lot to learn and we wanted to understand. So we did reach out with that statement. And basically, we had a lot of goals in doing so. We wanted to learn from people who had a connection to Mauna Kea about the issues that were important to them. Clearly, they had strong feelings, and we wanted to understand those feelings much better. Another thing that was important is that we know, and we learned from DKIS that it's, of course, and it's just human nature, that if you're going to be able to accomplish something, you've got to establish trust and you've got to build relationships, and they have to be authentic. So in order to do that, you have to get to know each other. And this was a way to start to get to know each other, as opposed to in some of these public processes, these formal public processes, people have 3 minutes to get up there and say their public comments, and that's that. You don't really have an opportunity to really talk to people. You do more so in the Section 106 process, where there are smaller groups and you can have conversations. And it's not testimony that they're giving or public comments that they're giving. It's a conversation about how to address adverse effects. But even that wasn't nearly what we were able to do in these meetings. So it was really quite an incredible experience that we had. Also, one of the things we wanted to make sure we didn't do was we didn't want to influence the ongoing Astra 2020 decadal survey process, which was ongoing. It was delayed, and we just wanted to be sure we didn't want to start a formal environmental review. In part, that was one of the reasons why we wanted to see what the decadal survey had to say about it. That's influential in what NSF does. NSF doesn't have to follow it, but it certainly is influential. And also, planning and design proposals do not trigger formal environmental compliance requirements. It doesn't. It would have to be something that would have to have an environmental impact in order for those federal statutes to kick in. So if you're planning, a proposal to plan something or design something doesn't have any on the ground impacts. Something that is a development or a construction, that sort of thing would. And also, it's important to us. Regardless of TMT or anything else in the future, we have 2 assets up on Mauna Kea right now. We have the Gemini North Observatory, and we have a very long baseline array antenna up there right now. So we saw that there were those protests and there were those concerns, and a lot of upset people and people who felt that they hadn't been listened to. And that was very concerning to us. And knowing that we had assets there, this wasn't something we thought we could ignore or should ignore. And so we thought it was very important to try to learn what was going on. So regardless of any future investment in another facility, we thought it was important to just figure out what was going on for what we have right now. Next slide, please. So these talk story sessions went on for about 16 months, from our August of 2020 all the way through November 2021. When November 2021 is when Astro 2020 came out. We met with people from all sides of the issue. We met with over 150 people. Probably, I would guess maybe closer to 180 by now, Dave, right? Somewhere around there. There were three of us that made up a core team. Dave and I were two of the three. We had a senior legislative affairs person as well, Karen Pierce, who joined us. Everything was held over Zoom due to COVID-19. And, you know, it has its benefits and downsides as well. I mean, obviously, not the same thing as meeting in person with people. That's a much more, you know, intimate experience when you can actually see people and you can read body language, and, you know, it helps to establish trust better when you're there in person. But everybody was on the same playing field because we all were dealing with COVID-19. People understood that safety was really important. And so this is what we all had to live with. And so that's what we did. The benefit was we were able to meet with more people. We didn't have to travel. So we were able to meet with an awful lot of people. And sometimes I remember our first meeting with a Native Hawaiian individual. She was shocked because she was expecting that this was going to be like all those public meetings and thought that there was going to be a cast of thousands to join us. And she found out she was the only one. And we met with her for about 4 hours. And she was incredibly appreciative, and it was really a great experience for both of us. The format was pretty much consistent with each meeting. We started out with introductions and explained who we were and our experience in Hawaii and what we were hoping to accomplish. And then we wanted to know about their connection to Mauna Kea, and they were very forthcoming about that. We wanted to know about what they thought about TMT being there, what they thought about that, if it was a positive, it was a negative, or both, and ideas for what it would look like to conduct a more meaningful environmental review process. I mean, we tried with DCAS to do as much as we possibly could to make it meaningful, to say, this is a great federal agency. I mean, NSF is an independent federal agency. Our directors serve 6-year terms over different presidential administrations. So we aren't as political as a lot of agencies are. We're not a cabinet level agency. So we have a little more flexibility. We can be a little more creative. And so if we wanted to tell people, and we did tell people that with DCIST, if you want an opportunity to try to connect and do something special with a federal agency, this is the agency to do it with. We made some progress, but we knew we had a ways to go. So this is what we heard. This was a word cloud that as of maybe midway through the process, I'd say probably more so. We had more meetings toward the first half of the time frame that we were involved in this. And this is what came through in the cloud, the word cloud. A lot of these themes that we heard, you know, culture and place were big. You could see Native Hawaiian people, outreach, all of these kinds of things. A lot of interesting themes that came about. I mean, we heard a lot of things about the young people, that there was more of a renaissance of culture from the younger people. That was an interesting thing to hear as well. And just people feeling like they hadn't been heard. The next slide. Oh, Dave, you might be muted.
Sorry about that.
That's all right.
So yeah, as Caroline mentioned, our informal outreach went through November of 2021, which happened to be when the decadal survey came out. And so it was anticipated, and you know, one of the reasons we did the informal outreach was because we thought that, you know, the TMT and GMT might come out near the top of the, as far as large facilities, large ground-based facilities would go, might come out near the top. And indeed, they came out as the #1 priority in ASTRA 2020. In addition to that, another interesting aspect, though, for the first time, the decadal survey weighed in they have been doing recently a state of the profession section for the survey. And in this state of the profession, they decided to weigh in on engagement with Indigenous communities. They saw this, especially with the protests due to TMT. And so one of their recommendations was that the astronomy community should, through the various societies, work with experts from other disciplines in order to come up with a community astronomy model of engagement that both is able to advance scientific research, but also to empower and benefit local communities, which is kind of the same. It aligns almost perfectly with what NSF was doing. We were trying to do with both with what we did with DKIST and also what we're doing with our informal outreach. So while all of this was going on, our informal outreach efforts, other entities were also trying to move the ball forward with respect to Mauna Kea and astronomy in Hawaii. And one of those entities is the University of Hawaii. They are currently the manager for Mauna Kea. They have a master lease with the DLNR, Department of Land and Natural Resources, and they take care of all of the astronomy observatories that are on top of the summit. They provide the logistics and the infrastructure for those observatories. And so they also took note of the protests and they wanted to engage the community more. And so they formed what they called their Center for Mauna Kea Stewardship. And this was part of their master lease and their master plan and their comprehensive management plan. All three of these documents were trying to engage the community more. And so in addition to the community, they also had, we had interactions between the University of Hawaii and the Mauna Kea observatories. And they were moving forward with things like sublease negotiations. All of the observatories, including NSF, have subleases with the university. In addition to the University of Hawaii, the state of Hawaii itself was also evaluating the situation on Mauna Kea and how things might be better. The first thing they did was they hired a consultant to go through the current state of Mauna Kea management and to evaluate the University of Hawaii's comprehensive management plan. This consultant, Don Chang, finished her final report in December of 2020. Shortly thereafter, the Hawaii Speaker of the House formed a Mauna Kea working group, and their task was to develop recommendations for and explore other options for governance and management structure for Mauna Kea. So and so they formed this 15-member working group in March of last year, and they presented their final report to the Hawaii legislature. This was incorporated into a House Bill 2024, this legislation. This House Bill 2024 was passed by the Hawaii State Legislature, and it's currently sitting on the governor's desk awaiting signature or veto. And it recommends a new Mauna Kea Stewardship Authority. And there would be if this were to pass, it would be a 5-year transition where the University of Hawaii would turn over the management of the Summit of Mauna Kea to this new authority. So I'll just go quickly, our status right now with respect to TMT and Mauna Kea. As we mentioned before, Astro 2020 came out. TMT is one of the #1 highest priorities for ground-based astronomy. We've finished our informal outreach, and if we decide to move forward with the formal process, which would be required if we were to get involved in TMT construction. We, after listening to the members of the Native Hawaiian community, we see that, or we realize that we would actually have to do something really creative, rather than just a no-go alternative for TMT. And that's where, as Caroline mentioned, the flexibility that NSF has as an independent agency would come in. And so we think that we could do, if we were to move forward, we would be very open to, creative thinking. And there'll be lots of opportunities for additional engagement with the community. And so finally, our last slide, and sorry for Claire for going over. These are just the conclusions. I'll leave these up here. But just say that, we realize that building telescopes in Hawaii is a sensitive issue with the local community. And right now we're doing our best to work with the local community. And we believe that the work that we've been doing has, aligns with the Astro 2020 Decadal Survey goals of, working with indigenous communities, so that, we can have we can have this model of mutual stewardship for this land. And that's beneficial to all, both the astronomy community and to the local communities that support us. And we probably want to save questions to the end, I'm guessing.
Yep. In the interest of time, we're going to move on to the next speaker and have questions at the end. So our next speaker is Dr. Claire Raftery.
Thank you. Can you let me know how much time is left in this session, just so I know how long-winded to be?
We have about 15 minutes left.
Okay, perfect. Well, thank you all for having me this morning. It's nice to be able to join you. My name is Claire Raftery, and I am the head of education, outreach, and communications for the National Solar Observatory, which is an NSF facility. We're based in Boulder, Colorado, and also in Maui, Hawaii. And the Daniel K. Inouye Solar Telescope falls within our remit. So I'm going to talk a little bit today about some of the efforts that we are undertaking in Maui in particular to engage folks around the Daniel K. Inouye Solar Telescope and the work that we're doing at NSO. So I wanted to begin by, I guess, acknowledging that when I was invited to give this presentation, I was not entirely sure what the most effective way to discuss this would be, because it's an enormous topic to discuss, and it's also, it's something that, as you've heard, is, it's difficult. There's a lot of uncomfortable conversations that have to happen. We are doing what we think is the right thing to do, but there is no set course for how to do this kind of work. And there's many, many different ways that you can go about doing this. So rather than describing all of our programs and going into the detail, because they're so niche for a very specific circumstance, what I wanted to do instead was focus on some of the things that motivate the decisions that we make in doing the kinds of programs that we do. So I'm going to be mainly talking about the ethos of the work that we do and how we decide to do them. So ultimately, we're a very privileged group to have access to such an incredible technological and scientific asset as the Inouye Solar Telescope. And with such access comes resources and money. And so I see it as our responsibility to identify ways to share those resources and those monies with the communities where the telescope is located, and to try and leverage it as best we can for the good of as many people as we possibly can. So I wanted to start out quickly with just a nod to the overall goals that we have for NSO's outreach team. Our goals include trying to highlight and promote the research that we do at NSO. We desire to become a nationwide leader in science engagement and education. We want to support the growth and development of the next generation of solar employees. And We want NSO to be recognized as a community-facing organization that's in support of education. And it's really this last goal that I want to focus on for today's conversation. And this is our sort of guiding post for when we make decisions on what to do and how we go about doing it. Does this help to reinforce the message that we are a community-facing organization and that we are in support of local education efforts? So the ethos of our work, the things that help us to decide what to do and how we go about doing it, more importantly. This is a laundry list essentially, and it is very far from complete, but it's just to give you an idea of some of the things that go into the decision-making process. So first and foremost, authentic partnership is essential. I think you heard this from Caroline and Dave earlier, that being able to build relationships with people is essential for doing any kind of authentic work. And for the kind of work that we're doing, supporting what already exists is a really valuable way to go about that. Not trying to reinvent the wheel, not trying to do something brand new, but there's already a lot of really great work out there. And how can we support it? How can we enhance it? How can we contribute to it? But we're not descending in to make things better. We are becoming a neighbor, and we're there to lift up the community as best that we can. A key way to do this, which should not be news for anybody who does this work, is just to bring your audience into the conversation as early as possible, to have them as a partner at the table, developing and ideating right from the very beginning. And I think that's really essential for any kind of effective engagement, whether in Hawaii or anywhere else. Another element that is particularly valuable in this case is sustained engagement. So not to show up once or to show up twice, but to show up every single time continuously and for as long as possible. This sustained engagement, becoming a reliable neighbor, as I mentioned earlier, I think is a really important aspect to this. So then we get into some of the more challenging ones. And I think that it's really important that we avoid getting into a deficit mindset when working with any kind of underrepresented groups. And what I mean by that is, rather than thinking about what is lacking, all of these communities are thriving as they are, and they have wonderful and unique things to offer. So what are those unique and important and valuable contributions, and how can we, as I said earlier, partner with them? How can we leverage that to do the very best for everybody that we possibly can? And I think that's something that is this idea of a deficit mindset is kind of the go-to a lot of the time, and trying to break from that to recognize that everything is an enhancement as opposed to a fixer, I think is a challenge, but essential for effective work. And that ties into my next point, which is that we also need to avoid any kind of saviorism, either white saviorism or any other kind, that we are not here to fix or repair or tell communities how to exist or how to thrive. They're already doing that already. They're doing great work, and they're thriving as communities as it already is. And so our presence on the islands is an addition to what is already there. And so avoiding this idea that we are here to give you good jobs. We're not giving good jobs, because good is an evaluation of some kind. Maybe we're providing high-paying jobs or technical jobs or long-term jobs. There are different ways to qualify this, but it's not our place to put a quality judgment on any of this, because that has implications for what was there before, and that isn't really appropriate for or beneficial to anybody. I also think that it's really important that you respect and believe in the culture of a place, even if it's not yours, even if it doesn't make sense to you. If you're talking about a mountain being sacred and it doesn't resonate with you, that doesn't really matter. That's something that is inherent to the place, that is important for you to acknowledge and for you to work into the efforts that you're making. Even if it doesn't come from you, I think it's really valuable and essential that that is a part of all of the work that you're doing. And it's not only the overt things like the sacred nature of the mountains, just the very, the the way life happens in Hawaii can be quite different to the mainland. And I think recognizing that is essential for any kind of success. I think it's really important that we recognize that we don't know best and that it's not our place to speak for others, and that it will never be appropriate for me to tell you what the opinions of a Native Hawaiian group is and why they're struggling with the telescopes. That's for the Native Hawaiian communities to talk about. And that goes back to the bringing everybody to the table and allowing people the space to be able to express themselves, but to bring as many diverse perspectives and voices into the conversation so you can have a kind of a broad understanding of everybody's perspective, and knowing that there isn't even a single perspective or a consensus perspective within Hawaii, that everybody has their own individual ideas and interpretations of things, and all of that is all completely valid. I've mentioned this a few times, be a good neighbor. We're arriving in a place, we're setting up shop, setting up the offices and the telescope, and integrating into the community and into the landscape. And so if you were moving into a new housing development, what would it mean to be a good neighbor? And they're just some of the fundamental philosophies. And then finally, to show up when and where you're invited. There is a lot of really excellent work already happening, as I mentioned, and we're very lucky to be getting invitations to participate and to come to events and to participate in things, and to be able to show up when we're invited and be an active member of the local community, I think is a respectful and sustainable way to show our support for what's already happening within the islands. So I'm conscious of the fact that we're very short on time. I had some examples of the work that we are doing at NSO, and I might just mention them very briefly. So we have teacher education programs, we have classroom visits where scientists and engineers go out to classrooms and talk about their careers, and we focus specifically beyond the PhD. So PhDs are the smallest number of professionals that we have at the telescope, and we really tried to highlight that in order to work at a telescope, you don't need a PhD in astronomy. There's lots of other ways to do that. We have an ongoing presence at many community events. We have 2 full-time staff out in Hawaii at the moment, and they're constantly flying around to different events on different islands to participate. We have an evolving partnership with the Haleakala National Park Service, which is relatively new, and the highlight of this so far has been the first Solar Week, which happened earlier this year. We're hoping this will become an annual event within the Haleakala National Park. And then we're looking for ways to provide opportunities for local people to access the telescope, to open the doors and to make it an asset for the local community. And we're following a lot of the good practices that the Mauna Kea observatories have already been doing in that regard. We're very early in that process because construction has only just ended. And so the rules around construction and the rules around operations will be hopefully somewhat different. But this is something that we're focusing on trying to do in order to help local folks feel like they have a sense of ownership or pride in the telescope. So I will leave it there, and then we might be able to squeeze in a few questions before we wrap up.
Thank you all so much. My question is for Claire. On one of your last slides, you talked about not speaking on behalf of the people whose feelings or thoughts are not your own, but being respectful about bringing them to the table, and which is a really great point. My question is, like in another context, we were taught earlier this week about being allies and speaking up for the underrepresented group. And that sometimes if you are in the majority, your voice is sometimes louder and maybe more impactful on the majority group who you're trying to influence. So I'm wondering if you have a comment, are there like different contexts or scenarios where you think we should speak up, or in general, your comment about, I guess, so maybe I'll end there. Does my question make sense? Do you understand?
It does. I do understand, and I recognize that yes, that allyship and intervention is also a really important part of advocacy. I still think that there's a difference between speaking on behalf of a group when you're not a member of that group and making space for somebody from that group to be able to discuss their thoughts and feelings. And I think that that's a really important distinction. And so in a case like this, it is important to have the conversation to say it is really important that both Native Hawaiian and Hawaii born and raised folks have the space to express themselves and express their concerns or support, or whatever it might be. But it would be inappropriate for me to try and articulate this is somebody else's opinion on this matter. Does that make sense? I recognize that it can be a subtle difference sometimes, but it is, I think it's a really important distinction that, perhaps another way to think about it is that, those of us who are in the positions of privilege can create the space and get out of the way. And, people don't need us to speak for them, but sometimes they benefit from us helping to create space in order to have their voices heard.
Yeah, that distinction really makes sense. Thank you so much for clarifying. I like that a lot.
Happy to do so.
Yeah, just to add to that, I'll mention that for our informal outreach, the primary focus, we did very little talking. Our primary focus was listening and just hearing what the community was thinking.
Thank you for the very nice talk. I'm from Alaska, and I was faculty there. I recently moved to Maryland, but just a month ago, I was in Alaska as a faculty there. And then I created my own education outreach program there. And our idea is going to these Alaska Native villages and installing the magnetometer so that we could understand what interesting space weather happens. But what I also learned is that there's a lot of tribes and they have all different cultures. So I'm curious how you guys approach all different tribes and understanding their cultures, and do you have any strategy? I mean, we still have a next leader, Doa. So she is now leading our education outreach program, and we would like to hear your know-how and how you reach these different tribes and their cultures and respect them. And I wanted to hear your advice.
So I'd like to share a little bit about the putting the magnetometers in the communities, and then perhaps Dave or Caroline might speak about the engaging with the people of different backgrounds. One thing that I would perhaps offer as far as best practices or lessons that I have observed with projects such as putting instruments in Indigenous communities is ongoing engagement afterwards. What does the community get from this instrument? Or is this a largely one-way transaction where you're getting scientific data and they're hosting the instruments? But this is where that authentic partnership aspect is really important, where having early conversations with the potential host communities to say, well, are there things that would be beneficial to you here? Are there resources and monies that we could bring to your community that would, with this as an excuse or as a conduit in order to be able to enhance and support what you already have going on or fill a need that you might have, as opposed to assuming that just the instrument itself will bring a prestige or an interest, because everybody is overworked and everybody is already really busy. And so expecting that there will be bandwidth to be able to absorb the benefit of that isn't always accurate. So just, this is not necessarily a comment on your project. I'm sure it's a wonderful effort and it's always exciting to hear, but more of a sort of a broader shout out to, working with communities to put instrumentation is really valuable and also requires a lot of additional thought. So Caroline or Dave, I'm not sure if you'd like to comment on the other aspect.
Yeah, I think I probably would be the one to do that. There are 574 federally recognized tribes, and and many unrecognized tribes. It would be impossible to know the culture of every one of those groups. The way we typically approach it, and I think people who work in this area typically approach it, is that there are some basic themes that are true for everybody that you deal with. And that is treating people with respect, listening to their concerns. As Claire had said, follow up, continue to talk with them, being transparent, establishing trust, building those relationships. If people understand what you are trying to do and you explain it to them, and you talk to them before you do something and help them to feel that they have a voice in this, and it's not just something that's being thrust upon them, then people might be willing to talk with you. And then maybe you can find out how might it benefit them, and what things might you be able to offer them, and how might what you're planning on doing benefit them. So it starts to build that relationship. But these are things that are about human relationships that really transcend every group, every person. Nobody wants to feel like they don't have a say in something that is important to them. And that's kind of what it comes down to.
I would also offer the idea that how important is it that there is a consensus. If you have, from what you described, a project where you're going into individual communities, having individual conversations with each of these communities is valuable in and of itself, and having a single homogeneous expectation likely won't be particularly successful, or may not be as successful as having a bunch of individual, but giving people the respect of a authentic and one-on-one kind of understanding.
And also recognizing in a lot of these, Alaska Native corporations and so forth, there is a form of government, and it's very important to make sure that you are dealing with the appropriate authorities. We've had a situation in the past where some PIs were dealing with elders, tribal elders, but they didn't have the authority of the tribe to carry out research, and that created a problem. So when you have a tribal government, it is important to make sure that you have the okay of the tribal government. In Hawaii, of course, that becomes more difficult because there isn't a form of government, and then it does become more difficult because one person may think one way, another person thinks another way, and it becomes very challenging to try to figure out which way to go. But I'd say it's very important to make sure that you're dealing with the appropriate authorities.
Thank you very much. This is great discussion that we will continue in the future. This is just the beginning of it. It's very important questions that we as scientists need to understand and better engage. So let's give a round of applause to our speakers.
Thank you.
Thank you.
Thank you. And now we have time for some brief announcements. And Chris also would like to share.
So you guys must have seen these things around the table, and I was asked to kind of say something about it actually, because I guess it was just sneaked it in on the table there and left it there. So we're thinking of leaving a little memento of our presence here. So I started with the obvious one, Summer Workshop 2022. Kind of, I was also there, kind of think, after all, we're not coming back here anytime soon. But the most important part is the reference, I think, to NSF and GEM, all right? NSF and GEM go hand in hand, all right? We will not be there here, we will not be doing what we do here without the support of NSF. And then I included the SBCCI, all right? This is the Community Cares Initiative that we started, a year ago, but I think it goes back to, around 2018. where other the chair of Jacob and the leadership of Paul. I hope Paul is here somewhere. They started talking about community issues as well. And in 2018, we had, I don't know if you remember, the microaggressions event that was organized there. 2019, again, under the leadership of Paul, we had the underrepresented minority event, and then of course COVID era kicked in, and things changed a lot, and it became even more obvious, you know, that we need to care about our community, and events took place, and I think this need to care about our community kind of blew up, and now the way I look at it is that GEM is a three-legged entity. It's a plenary where it's like more of a looking at where we are and what we're doing, and it's of course all the research, you know, all the concurrent sessions, the focus groups, all that difficult work, you know, pushing the boundaries of research every day. But I think the community cares initiative should be an equal and third leg. It's like of the three-legged stool, you know, that's the only way you can really get balanced, and we need that. And we named it in honor of Pham, the Pham Become Community Cares Initiative. And on Friday, we're going to talk a little more about it after the social after the end of the meeting. We're going to have a small goodbye social, and we have here Pham's parents who wanted to kind of thank you for all the support for all this year. I mean, for the past 2 years, and I think we're going to talk about it a little more there. Okay, thank you.
Okay, Vanya already gave an announcement, but the GEMI student lunch today, we're inviting anyone who would like to have signed up for being a mentor but didn't have quite the time and commitment. So if you are interested in group mentoring students, please come to the lunch. And students, if you didn't sign up for the mentoring program, but you would like to be mentored, please come to the lunch. Everyone who would like to participate is invited. Thank you, Hyunju, for organizing. That's the announcement. 12 p.m. and that's here. Yeah.
Next room.
It's in the next room.
You can smell the food.
Yeah.
I'm sure you're very busy.
So our retention battle focus group is having our final standalone session this morning, just next session in the same room. So we're going to have 2 exciting talks about the future direction of inner magosphere research and exploration, led by Dr. Chini Lee and Vanya Jordanova. So please join us for this rich open discussions. And we also have a joint session this afternoon with Cold Plasma, SHIM, and also MPEC focus group. I will lead that introduction to them.
We invite you to join our reconnection session. We will have 2 sessions this afternoon in the Bluefin room. Today's focus will be the global aspect with speakers and discussions about global models and the vision opportunities of MI coupling related to reconnection. You may already had a flavor of that from John Dorelli's nice talk on Monday. If you like it, we will have more in our sessions. Thank you.
Hello, if you would like conversation, please come to the Stingray room today. We have 3 sessions from the Modeling Methods and Validation Resource Group. At 10:30, decadal survey white papers related to modeling. We only have half a dozen. There will be plenty of time for conversation. 1:30, we have picked out 3 for dedicated real-time brainstorming and outlining. Lots of time for conversation. In the 3rd session, we have recent developments in methods and validation. Only half a dozen talks, plenty of time for conversation in the Stingray room.
We will have the 3-dimensional ionosphere atmospheric electrodynamic coupling of the magnetosphere, ionosphere, thermospheres standalone session right after the break at the Bluefin room on the 3rd floor. This is the last standalone session of this very valuable focus group that is led by Dr. Hunju Kanner. So we are all waiting you at this session so that we will be concluding with a community discussion, and we are hoping you'll be there.
The first focus group, self-consistent in the magnetosphere modeling, will have 2 joint sessions in this afternoon. Both of the sessions will be in the 6th floor. And the first session will be in the joint session with MPC, which starts at 1:30. The second joint session is the joint session with RB Berlin Belt, called Plasma, and at MPC, and the recurrent session. Look forward to it.
Okay, thank you. So I'm one of the focus group leaders for the impact of the cold plasma magnetospheric physics. So we begin today at the last session, which is joined with some of the other focus groups, and the topic is the impact of the impact of the cold plasma on wave particle interactions. So we'll have a scene-setting talk given by Jacob, and then it's actually geared towards students, and then a bunch of contributed talks. So I hope to see you in the afternoon.
Great, thank you all. So let's have a little coffee break now.